I've just finished an analysis that I've been wanting to do for a long time, which is there's this idea that's been around for quite a long time. A lot of ideas in space have been around a long time. It's one of the odd things. They keep coming around. Anyhow, the idea is let's put solar panels in orbit. Hey, sounds like a great idea. You know, the sun is there all the time, 24 hours a day. The sun is brighter in space. You don't have the atmosphere filtering some of the light. It's like 40% brighter. The days you get, on average, maybe 23 hours of sunlight in space. The spacecraft will be eclipsed by the Earth every so often. But by and large, 24/7, bright sun, put it up in space. It's got to be way more efficient than having it on the Earth. You have to put it in a geosynchronous orbit, 22,000 miles from the Earth. Okay, no problem. We'll beam the power back to Earth with microwaves, and we'll put a mesh somewhere in some uninhabited part of some uninhabited state, and we'll beam back megawatts of virtually free electricity. I mean, that's an idea that I remember as a kid reading popular science. This has been around a long time. Okay, so I wanted to run the numbers because it's always kind of didn't seem right. I mean, I designed spacecraft for a living. I know how hard and how expensive it is to do that. And it's like, this thing's going to have to be huge. And it's going to have to be, well, expensive. And it has to be cost competitive with something that's installed in Arizona in the desert. It's going to have to be cost competitive with installations in other sunny parts of the world. Okay, so here's some of the numbers. First of all, I was working with just a sort of a standard size, a square kilometer. That's about enough to produce 0.07% of the United States consumption of electricity. But okay, it's a start. It's a number. We'll work with a square kilometer. That will weigh 8,000 metric tons installed on the Earth. And you can say, well, maybe we can make it a little bit lighter in space. Well, if you want to make it lighter, it's going to cost more. And you really can't, because these things have to be able to survive launch vehicles. And launch vehicles shake the hell out of everything. And so the comparative structure to building something, a solar array, in the desert that has to stand up to the Earth's gravity and to wind and whatever, it's comparable to what the structure would have to be in terms of mass in order to survive a launch. So, okay, so it's going to weigh, this array is going to weigh 8,000 metric tons. Now, to get it to Arizona or Nevada or Utah or some other sunny part of the country, and assuming that they're built in China, which is the low-cost source for solar arrays, the shipping cost is about $4 million to ship from China to the U.S. We won't talk about installation cost. We won't talk about, a lot of different costs. We'll just say, we'll talk about just shipping. Just shipping. Okay. Not assembly, not, hooking it into the grid, not the lawyer's fees, not the insurance, just shipping. $4 million to produce a 1 square kilometer array in Arizona, okay, or New Mexico, or someplace else that's sunny. To get your 1 kilometer array into orbit, into geosynchronous orbit, you're going to need launch vehicles. Now, the number I realized I'd put down here was the cost to get into low Earth orbit. Geosynchronous, it's going to be like twice as much as the numbers I'm about to tell you. So, the Falcon 9 per launch, give or take, is about $50 million. Give or take. They quote different numbers. That's probably their absolute bottom line cost. And the Falcon 9 can put 10.5 metric tons into low Earth orbit. It can probably put about half of that to geosynchronous. But talking about low Earth orbit, okay, so 10.5 metric tons to put per launch means that you're going to have a lot of launches to put 8,000 metric tons into orbit. In fact, it's 765 Falcon 9 launches. And if you multiply 765 by 50 million, you're up around $38 billion to launch your 1 kilometer square solar collecting spacecraft, assembled in orbit, of course. Okay, so it already doesn't sound too good, doesn't it? It's like, okay, from China, it's $4 million to have it shipped to an installation, and into orbit, it's going to be 38 million. Oh, I forgot. That's right. It's more efficient. It's more efficient to put it in orbit. It's 6 times more efficient because you've got more days, more hours to the day, and a brighter sun. Okay, so you're going to have 6 times bigger array in Arizona to make up the difference. So instead of 4 million, you're talking about what's 6 times 4? 24 million for shipping versus 38 billion. Okay, so we still have a problem. Even though we're more efficient, that shipping cost up to orbit is a lot more than our shipping cost from China to the desert southwest of the United States. Okay, let's look at a little bit more detail here. Okay. Well, the additional detail really is that 0.07% of the United States power consumption, to produce that and spend $38 billion just to ship that up into orbit, not any other cost, that's really painful. That's really painful. The array itself would probably cost, just the solar collectors would probably cost about $250 million. And space rated, it's going to probably have to be a lot more than that. But the Earth, at least the Earth version, will be about $250 million just for the solar collectors per square kilometer. Okay, so I add up all the numbers, multiply it out, and then ask myself a simple question. It really isn't worth doing unless you're going to produce a substantial proportion of power. The usual sort of trip point where people start to say that something's worth doing as a major initiative in power production is 10%. If we can produce 10% from wind, if we can produce 10% from solar, if we can produce 10% somehow, it's maybe worth thinking about. Okay, so how much would these launch costs, would it cost to produce 10% of the United States power consumption, electrical power consumption from orbit? And so here we go. You're going to need 144 square kilometers of collector in orbit, which is about the size of a good-sized New England town. That's 14 by 10 kilometers, that rectangle 14 by 10 kilometers. The mass of this will be 1.1 million metric tons. Okay. And you divide 10 metric tons for each Falcon launch into that, and it's 110,000 Falcon 9 launches in order to put this thing into orbit, in order to put 10% of our national consumption of electricity, power production, into orbit as a solar collector. Okay, so let's see. We were talking about $50 million per launch. Multiply it out. $5.5 trillion to launch those 110,000 Falcon 9s. Okay, well, this is starting to sound a little absurd. Of course, if we're going to make that many launches, we're going to get the cost down on the launch vehicles. We're going to be building these things like Chevy Cavaliers. Of course, okay, launch vehicle cost goes down. But remember, I said 10 metric tons to LEO, to low Earth orbit. To geosynchronous, it's going to be a lot more like 5. So, a lot of things are going to work in the wrong direction. So, yeah, you can maybe get some economies of scale by building lots and lots and lots and lots and lots of rockets and launching them, 3 or 4 or 5 or 100 times a day. Okay, maybe you could figure it out. Maybe you could drive that 5.5 trillion down to 2 trillion. Oh, yeah, we're going to... But there's a problem, is that the amount of power that you can produce and sell, you have to sell this power at an affordable rate. The power companies aren't going to buy it if it doesn't cost 10 cents a kilowatt hour, something like that. So you start selling your power from your space-based system at 10 cents a kilowatt hour to the power companies. You manage to pull it off, you manage to install it, you manage to hook it into the grid with some sort of a mesh system that collects microwaves from orbit and start selling it at 10 cents a kilowatt hour. Well, guess what? You start putting those 10 cents per kilowatt hour into the bank to pay back your investors. It's going to take 126 years to get all of the money back to pay for that solar cell collecting system, just to break even, just to pay for it, before your investors start making any money. Now, there's a number of problems with that. And first of all, 126 years from now, all of your investors will be dead. Another problem is that your solar collectors lose about 2% of their ability to convert photons into electrons per year. The sun wears these things out, and the sun in space particularly wears these things out. So they're only good for 10 or 20 years. So, I mean, all the way around, you're just so far apart if you think you can pull this off. You're so far apart, no matter how much you put up there, it's going to cost, 10 to 20 to 50 times more than it would cost to build a similar system on the Earth. And somebody's going to have to pay for that. It's not going to come, the Wizard of Oz is not going to pay for it. The Easter Bunny's not going to pay for it. Santa Claus is not going to pay for it. You've got to understand it's going to cost too much. So anyhow, phone is ringing, time's up. Hope you get the point. Take care.